So, um, we have a lot of issues that are coming up here. I didn't see too many. I didn't see any questions on the discussions board asking for some specific materials and things like that. But I know we need to prep for the exam this week, and we have our projects for the following week. So I want to do just kind of a quick summary of some of the stuff that. Let me turn on recording, make sure recording's turned on, so you guys that can't make it, weren't able to make it, or if you guys want to see something you want to replay later on, you'll be able to get to it. Um, the exam's coming up this Tuesday, and we have a project the following week. I know the projects that you guys are concerned about, like correlation, regression, particularly logistic regression. I'm not so sure that the most advanced of that stuff will be on the exam, but certainly we're going to be covering a lot of the material that we learned about since the exam one, which is considerable. I mean, it goes back quite a ways. And I just want to review some of that material to make sure that we're all on the same page on that stuff, particularly since I haven't gotten any specific questions about material that you wanted to cover tonight. If you have something that you have an issue with, type it into the chat box. And I think we're a small enough group that I can maybe turn on a mic or two if I need to, so that if you want to ask it verbally, you can ask it verbally as well. Oh yeah, there's two groups here. There's the online group where the exam was due tonight, and if you didn't get both attempts in, I may maybe relax that a little bit with some small penalty. But yeah, you're right. You're right for that. In fact, you should be doing it now, right? Because you need to start at 9 to get a full 3 hours. I know I think you won't need that much time. But there's another group that's likely to be online, which is a brick and mortar class, and they are mirroring the same material, but they have an exam in class on Tuesday night. That's what that's all about. Sorry, I forgot that I might be talking to two groups of people and confusing both of them. Oh, good. Okay, good. All right. So if you have a question or something like that, they can ask and that I can answer in a general manner rather than a specific matter. I'm certainly willing to do that. So let's start from where we might begin at the earliest, as far as the exam two is for. This is mostly for the people that will be taking it on Tuesday night, and mostly review for you guys that in the online class at this stage. So for starters, you might want to just go back and remember how we use the empirical formula and the z-table to determine what the areas are in the normal distribution. So that if I asked you to give me the percentage of a population that was below a certain value, given that the mean was such and such and the standard deviation was such and such, determine the z-score. Once you've determined the z-score, then figure out the areas below the curve. You could use Excel. You could use the z-table to figure that out. Then also you want to make sure you're comfortable calculating t-scores. And I don't have. I'm going to hook up my. Give me a minute. I'm going to hook up my graphics tablet so I can do some writing. So I'm going to pause for a minute. Okay. Okay, so we know that we started with the normal distribution, right? It's basically bell-shaped curve. We know that if we have a mean, say this is a mean of 100, we have standard deviation of 10. These are population parameters, right? Because it's mu and sigma. We know that we can use the z-table to determine, well, let's see, the z-score of this value, let's say it's 90, is equal to 90 minus 100, right? In other words, x minus mu over the standard deviation, which is 10. There's going to be one standard deviation. We know that that's z-score. That z-score minus 1 represents a certain area to the left that we can look up on the table, so we can determine the various areas. So you might want to review a little bit of that. In addition to that, we know that when we start to deal with, instead of the normal distribution, we start to deal with the sample distribution. In other words, it's the distribution of samples, repeated samples of the same size over and over and over again, right? Well, let's say that now that our mean sample is going to equal about the same thing, 100, roughly 100, and the sample size is equal to, let's say 20. Let's say I'll make it a little bit bigger. Let's make it 100. We know if we take repeated samples of size 100 from a population that has a standard deviation of 10, we know that the standard error, the distribution of the samples that are taken, the repeated samples that are taken, is equal to the standard deviation over the square root of the sample size, right? Or 10 over 100. Square root of 100 is 10, so that's equal to 1. So we would expect that one z-score below the mean would be, in this case, would be, instead of 100 to 90, would be 100 to 99, right? Just one value below that. And 101, we would expect, for instance, 68% of these samples of size 100 from this population we described before to be between 99 and 101, right? So you want to remember how the sample distribution, the calculations based on a sample distribution work. The next thing we're going to need to remember is that we took this one step further and we said, well, what if we don't know what sigma is? What if we don't know what the population standard deviation is? And we're forced to, based on our sample, to use the standard deviation of the sample instead of the standard deviation of the population to calculate how our samples are distributed. So let's say our standard deviation is 10 instead of our sigma, instead of our sample standard deviation is 10, and our sample mean is, say, 100, right? And we want to know if how lucky we were in calculating in figuring out what the population mean is, how close we are to the population mean, since we only have the sample mean to work with. And what we do then is, let me get a fresh piece of paper. And what we do then, of course, is that we use a t-score instead, because a t-distribution will make up for the error that we've introduced by not knowing the population standard deviation. So let's see, if our sample mean is equal to 100, and our sample standard deviation is equal to 10, and our sample size is equal to 100, well, we say to ourselves, our confidence interval is going to be equal to x bar plus or minus, get the sample mean, plus or minus, well, it's a large sample size. So large sample size, we're not so worried about the standard deviation being used as a substitute for sigma. So we might use 1.96 for a 95% confidence interval, just like we would if we do the population standard deviation. Okay, and then we multiply that times the standard error, which in this case we'd have 100 plus or minus 1.96 times the standard error, which is 100, which is 10 divided by square root of 100, which is 1. So it's 100 plus or minus 1.96, right? Or roughly about 98 and 102, roughly, right? Well, if this sample size is not that large, if that sample size were, say, 25 instead, well, we have a little bit more error that's involved here now, right? Now, we're going to say x bar plus or minus, and I'm going to hold off on filling in the z-score here for a second, times the standard error. Well, in this case, standard error is equal to 10 divided by square root of 25, which is equal to 10 over 5 is 10 over 5 is going to be 2, right, times 2. And the z-score that we're going to use, well, you know, we can't really use the z-score, right, because the sample size is small. So using the standard deviation for, in the place of sigma, in order to calculate standard error, introduces a bit of extra error for us. So we used to have to use the t-score for 24 degrees of freedom, right, in order to figure out what our 95% confidence interval is going to be. I could get that from Excel, or I could get that from the table. Okay, let's get aggressive. I'm just using aggressive, of course, because it's on my computer. Let's see if I can't find it. Okay, let's see. Boy, oh boy, let's see. Here it is. Okay, let's see what it is for 24 degrees of freedom. For 24 degrees of freedom, let's see. A confidence interval is going to be 95% confidence interval is going to be down here somewhere, and 24 is going to be 2.064 is what we're going to use for our, in place of our 1.96, our p-value, 2.064. So it's going to be 2.064 times 2, right? Plus add and subtract it from 100, our mean, plus or minus 2.064. I'm going to call it 2.06. Is going to be 4.15, I'll call it 13, okay, roughly. So our 95% confidence interval using the t-score now is going to be roughly little under 96, 95.87 to 104.13 roughly, right? So I have to remember to use my t-score, how to look up my t-score, and how to figure this out. Okay, so the next thing we moved on to, after we got through confidence intervals, is, well, actually, before I move on to that, we also did this with proportions, didn't we? Okay, so maybe we better be prepared for the exam in case somebody asks us to find a confidence interval for a proportion. Okay, so how would we do that? Well, it works exactly the same way, right? We are interested in knowing what the population proportion is, P, but we really never, just like mu, we never really know that, just as we didn't know it in the last example. However, we might know what our sample P is, what the proportion for our sample is. For instance, let's say if I asked you to take a sample of 1,000 people, and I asked you to survey those 1,000 people and find out how many of them like broccoli, really like broccoli, right? And you said, okay, you surveyed those 1,000 people, and you found out of those 1,000 people, 150 people like broccoli, right? So that's 150 like broccoli, 850 don't like broccoli, 150 out of 1,000. That tells you that the sample proportion of people who don't like broccoli is equal to 15%, 0.15. Okay, so that's our sample proportion. But, you know, I want to know, you know, I'm a major broccoli farmer. I want to know what is the true proportion in the entire United States of people where this sample is drawn from. What's the true proportion of people that don't like broccoli? Well, we'll never know that, but we can create a confidence interval for this value. So one of the rules that we have when we create confidence intervals with proportions is it has to be a large sample size. And in that large sample size, each side of this has to be at least 15, right? So in other words, if we took a sample size of 100 and we had 12 people that were left-handed, let's say out of 100, and 88 that weren't left-handed, well, we got a sample size of 100, but we need both of these results, the yes and the no, the 1 and the 2, to be both above 15 in order for us to do this calculation, right? So that wouldn't work. If it turned out 20 and 80 out of 100, 20 were left-handed, 80 out of, that would work for us, but with a too small a sample. But this one doesn't have that problem. We have a lot of people. It's a big sample, 15,000 people, and so on and so forth. So how would we go about calculating its confidence interval? Would we do the same way as we did before? We would say that the 95% confidence interval is equal to p cap plus or minus, well, since it's a large sample, and remember, whenever we deal with proportions, we're always going to limit our analyses to large samples. So I'm going to use 1.96, the value for z, rather than worrying about t, times my standard error. So what's my standard error going to be equal to? I know what p is, p cap is. My standard error is going to be equal to the square root of p times 1 minus p. And we're, of course, going to use p cap here because that's all we know, over the sample size. So our standard error is going to be equal to the square root of 0.15 times 0.85 over 1,000. Okay, and then they take square root of that. So let's give that a try. I'm doing my 60-minute second half of the semester in biostatistics race right now. 0.115 times 0.85 is equal to this, divided by 1,000. It's equal to that. Find the square root of that. And it's equal to 0.11. I'm just going to call it 0.011. Okay, so this is going to be 0.011 times 1.96. Of course, you should keep track of your, not round until you're at the very end. So it's 0.15 plus or minus 1.96 times 0.011. Okay, so what is that? Let's see. Let's calculate this. So I'm going to clear my memory here. Remember to clear all. So 1.96 times 0.011 is equal to about 2%. I'm going to put that into memory. Okay, and I'm going to clear this. So now I'm going to take my 0.15 and subtract that number, which is what we would call the margin of error. Subtract the margin of error, and I get 0.128 is my lower range. I'm going to clear that and go to 0.15, and I'm going to add my margin of error. And that comes out to 0.1716. So between the true population proportion, based on this sample size and this result, the proportion in our population was 15%. The true population proportion, we're 95% confident, is between 13% and 17%, roughly. Okay, so that's the way we would deal with that. So next thing that we covered when we were dealing with these kinds of situations is we were concerned, well, what if we take a sample and compare it to a known number, or we compare two sample means to one another? Okay, we know that what we did there was we looked at this from the perspective of the means, comparing the means, right? Two numerical variable in two groups. So, for instance, if I wanted to compare the mean of mean of group 1 to the mean of group 2, I would create a hypothesis, a null hypothesis. And I would say let's start off with the null hypothesis that the two of them were equal to one another. And then what I would attempt to prove is that I can reject that idea and say that there's a difference between these two means, right? And the way that we're going to do this is we're going to use a test called the student's t-test, right? In which we compare these two means in terms of the number of standard deviations, standard errors, really, that they are apart. So I'm going to use, I think for the most part, for the exam, It's unlikely that you're going to wind up using, you're going to calculate this by hand. So I'm going to use SPSS, and I'm going to take a typical example that we were working with in SPSS in our, let's see, NC birth files. NC birth 800.SAB. Okay, hopefully I can open this. And I am going to, yes, I will definitely post this to Blackboard. See, I don't know if you can see that, but it's recording right here. Okay, so, okay, open data, yes. And hopefully it opened. Okay, and it's been doing this funny thing where it kind of hides itself like that. Okay, there we go. So I'm going to take a numerical variable here. For instance, the birth weight of the children in ounces. I'll use ounces because numbers are a little bit simpler. Okay, birth weight of infants in ounces, and I'm going to compare them for married versus unmarried women. Actually, before I even do that, I am going to say, let me just do a quick analysis here and analyze descriptive statistics. And I'm going to go into descriptives, and I'm going to ask it for what is the average birth weight of children in this study. Just want to get a quick look at that. The average birth weight in children in this study was 116 ounces, right? So I'm going to say to myself, that's interesting, that's great. But now I want to know if there was a difference in birth weight between married and unmarried women. Okay, but even before I do that, let's say I want to compare this. This is North Carolina. I want to compare the birth weight of this sample of women, the women from this population in North Carolina, to another population. This is a sample of women from North Carolina giving birth in 1 year. But let's say that another state like New York has more public health money, and they measured all of their tens of thousands of birth weights. And they actually have the actual mean for that entire population. It turns out to be 120 ounces. Let's say I want to compare our mean, our sample mean, which is roughly about 116, to the New York State population mean, which is 120. So it's a known value. So our null hypothesis in that case would be, let me bring this up. Our null hypothesis in that case would be that the mean for North Carolina babies is equal to the same as New York, 120, or the mean for North Carolina babies is not equal to 120. That's called a single sample t-test, right? Because we're comparing it to a known value. So I'm going to go in here and I'm going to actually give that a try if I can find it. Lung cancer, what happened to it? Went away. I have to reopen it. Open. Where'd it go? Where'd it go? Where'd it go? Open. Where is this? Here's some of your data files. I don't even see it there. Okay, I'll open it again. Oh, it's opening up in another version. It's opening up another copy of SPSS, but that's okay. 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 All right, there it is. So I'm going to go up here to Analyze, and I'm going to compare these two means. So I'm going to go down to Compare Means. One sample t-test. Remember, it's only one sample. The other value is already known. So I'm going to move in the birth weight of babies in this study in for North Carolina, and I'm going to compare it to the known mean of 120. I'm going to click OK. My output window will open up, and in my output window is a t-test. And I see that the t-score tells us that there's about 4.5 standard errors between these two means, right? And that the probability that we would be wrong if we reject the null hypothesis, or the probability that these two values came from the same population or had the same distribution, is well less than 0.05. So this is my p-value. As long as that's less than my alpha, my acceptable level of error of 5%, I can reject my null hypothesis and accept my alternative hypothesis. Let's take another look at this. Let's say I want to compare two different groups. So let me compare means, except this time I'm going to look at two independent groups, married women versus unmarried women. So I'm going to move my weight, birth weights, into my test variable. Okay, let's see. Weight of child in ounces. Okay, my grouping variable is going to be marital status. And I have to tell it what the numbers are that represent marital status. I think it's 1 and 2. I'm going to put in 1 and 2 just for the hell of it. But I think it is. Let's see if it works. And indeed, it did work. And what I found was that these two values are also very far apart. So, as a matter of fact, you can look here. And with not married women, the average birth weight was 109 pounds, 110 pounds. And for married women, the average birth weight was almost 120 pounds, quite a big difference. And if I go down here to my t-test, I can see, I'm going to use the bottom line here, I can see that the t-value is quite high. It's 5.5 standard errors apart, these two numbers. And the probability of being wrong if I reject my null hypothesis and accept my alternative hypothesis is going to be less than 5%. So I can go ahead and do that. Okay, and again, the hypothesis where, let's go back here. In this case, the hypothesis was this first one, that mu for unmarried women is equal to mu for married women, and our alternative hypothesis, mu for married women is for unmarried women is not equal to mu for married women. Right? So since we didn't know what the true population mean was for either of these. Okay, so that's the way we would deal with our. Now, the only other one that you're likely to come across is if you have a situation with paired samples. Let me see if I have samples. I wonder if I have one that I can find quickly. Nah. Paired sample t-test. Maybe there's one in here. Oh, okay, here we go. Let's try this. Okay, it opened it up successfully. In this one, we looked at the cholesterol drop if you ate cornflakes versus if you ate oat bran every morning for a month, let's say, right? And there's actually the same person. This is one subject. That's subject number 1, number 2, number 3, number 4. And he ate cornflakes for a month and then ate oat bran. And number 2 ate cornflakes for a month and then ate oat bran. They might have done them in the other order. They would have randomized the order. So maybe number 3 ate oat bran first and then ate cornflakes. And this is the drop in cholesterol that we saw from their normal cholesterol when they were free feeding on whatever they wanted to eat for breakfast. Okay, so we're going to look at what the difference is between these two values given that they're from the same person. So that's a paired sample. So if there's no difference, if our null hypothesis is that the average cholesterol drop for eating cornflakes and eating oatmeal is the same, then we would expect the difference between these two to be equal to 0. So in these paired samples, really what we wind up doing is doing a t-test where we're comparing the value, the difference in the results for each person to 0 to see if there's a difference. So in other words, our null hypothesis for this would be the difference in the cholesterol levels. The difference is equal to 0. It would be our null hypothesis. And our alternative hypothesis would be the difference is not equal to 0. So in Excel, in SPSS, we would go to Analyze, Compare Means, and we would go to Paired Sample t-tests. And we would put in our two values. This is for cornflakes. This is for bran flakes, I guess. And then we would go ahead and run our t-test. We run our t-test, and the average reduction in cholesterol for cornflakes was 4.08, and for oat bran was 4.4. right? And we look, the difference is, the average difference is, let's see, okay. So we go down here to our t-test, and we find that our t-test value is equal to 0.3344 and 13 degrees of freedom. Since this is a more small sample, SPSS used the t-test, not the t-value, not 1.96, and 13 degrees of freedom. And in order for us to reject the null hypothesis that there's zero difference between these two cholesterol reductions, we would have to have a significance of p-value of less than 0.05. And since we do have a p-value less than 0.05, we can reject the null hypothesis that the difference is equal to zero and accept the alternative hypothesis that the difference is not equal to zero. It's equal to something other than zero. Paired sample t-test. Okay, so the next thing we might run across a situation where we have two categorical variables, right? And those categorical variables, I have one that's open here. As a matter of fact, I'll use that. In this one, I have a categorical variable where I have an exposure to, say, asbestos, and I have perhaps union health data or something like that. This is a retrospective study, and I have historical data on workers in a plant that were exposed to some cancer-causing agent, nickel, cadmium, asbestos, benzene, whatever, right? I think in this one I called it asbestos. It really doesn't matter for our purposes. And there were 4 levels of exposure. No exposure, maybe workers that worked in some other area of the plant, a low level of exposure, a medium level of exposure, and a highest level of exposure. But it's categorical data. We don't know, we don't have an exact number, but we knew relatively what their exposure was. And we also have data on whether after 30 years, based on union records, whether or not they developed lung cancer or not. So if I look at this variable, we'll see that for the variable exposure level, we have 4 values, 0, 1, 2, and 3. For the result variable, right, the independent variable, we have 2 values, 1 lung cancer or 2 no cancer. Okay, so let's first organize this data. We go back to the data view. Let's first organize this data by going to Analyze, going to Descriptive Statistics, and crosstabs, because we're going to organize it into crosstabs since it's categorical data. I'm going to put the exposure in the rows. The exposure level goes into the rows, and lung cancer is going to go into the columns because that's the result or the dependent variable. And I'm going to ask it to calculate for me the chi-square value. I'm also going to ask it to I'm going to go into cells and ask to calculate the percentages by rows. And I'm going to click OK. Okay, my output window comes up, I hope. There it is. And here's my counts, right? I had 175 people who had no exposure, and 2 cases of in that group developed lung cancer. Among the low level of exposure, I only had 1 case, but that was only 43 people in that group. Medium level, I had 4 people and 52 people in that group. And the highest level of exposure, I also had 4 cases, but there were only 33 people in that group. So what was the risk for each exposure level? Okay, well, let's say for no exposure, 2 out of 175 is a risk of 1.1%. For lowest level, which is 1 out of 43, is 2.3%. And for the medium level, 7.7%, 4 out of 52. For the highest level of exposure, 12% of the people that were exposed to that level, although there were only 33, 4 of them, 12.1% of them developed lung cancer. Or 11, what was that, 11? Right, 4, right? This is the overall rate. The overall rate was 3.6%, right? That was the prevalence in this whole group. So at any rate, so I could see that as the exposure went up, the risk went up. Now, is this statistically significant? What's our null hypothesis here? Our null hypothesis here would be that that there is no association between exposure to this contaminant and lung cancer. And our alternative hypothesis would be that there is an association between exposure and lung cancer. Well, with chi-square, we know we can calculate it. This would be a 2 by 4 table, which would be 4 minus 1 is 3, 2 minus 1 is 1, so 3 times 1, this would be 3 degrees of freedom. So if I look at the chi-square calculation, indeed it's 3 degrees of freedom. My chi-square value is 12.5, and my significance, my p-value, my probability of being wrong if I reject the null hypothesis, is less than 0.05. So I can reject the null hypothesis that there's no association between exposure and the outcome of lung cancer, and accept the alternative that there is an association between exposure to this contaminant and lung cancer. So the only thing that would be even nicer is if I could go ahead and I could do a calculation that shows odd ratios for this as well. You know, in order to do that, I would have to restructure this data a bit. I could either filter it or I could create a new variable. So for instance, if I go in here to a no exposure and 0, 1, 2, and 3, let's say I want to compare 0 and the highest level of exposure to see what the relative risk and odds ratio were for this and see if it's statistically significant. Okay, well, what I would do is I need this a version of this variable that only has no exposure and the highest level of exposure if I want to compare just those two. So I'm going to create a new variable. I'm going to transform. I'm going to recode into different variables, into a new variable. And I'm going to take the exposure level, right? And I'm going to say I want to take the variable 0, and I'm going to keep it 0, right? I'm going to add it, so that's in my new variable. And I'm going to take the exposure 1, and I'm going to make the new value, I'm going to take the exposure 3, the highest level of exposure. I'm going to call that 1. So that's going to be recoded into 1. And those are the only two variables I'm going to move over into my new variable, right? And I'm going to call this new variable exposure, whoops. Come on, let me type. Oh, why is it letting me type? Oops. Continue. Oh, that's why. Okay, my output variable is going to be exposure none to high, highest. Pretty self-explanatory, right? And I could give it a label too if I want. I'm not going to bother. I'm going to create that new variable, and we'll see that now there is a third variable here. There's our third variable, right? None to, and I have to recode that now. That 0 represents no exposure, right? And 1 represents a high level of exposure. Okay, and I'm going to repeat my chi-square now, except only with those two variables, only with those two values. So I'm going to say analyze descriptive statistics crosstabs, and now I'm going to do, I'm not going to use that one, I'm going to use highest, none to highest, and lung cancer, I've only got to compare those two. I'm going to do chi-square, and this time I'm going to do risk, so I get the odds ratio and relative risk too. And in cells, I'm going to say, I'll just leave that the way it is. I'm going to say OK. Okay, let's see what our output looks like. Well, in this case, we only have two variables here, no exposure and high exposure. And as before, we got the same percentages by rows, right? 1.1% versus 12% for the people with the highest exposure. So let's see what our chi-square test says in this case. Well, a chi-square test, the value is quite high, and we can still reject the null hypothesis that there is an association. We can reject the null hypothesis that there's no association between exposure and lung cancer, and accept the alternative hypothesis there is an association between exposure to this contaminant and lung cancer. Not only that, but I can also now go down here and I can realize that the odds ratio for exposure to the highest level is going to be 0.084. You know, what happened here was The lung cancer is on this side here, and no cancer is on this side here. So our odds ratio is going to be, let's see, it's going to be, well, because I put assigned no exposure to value as 0 and high exposure to value of 1 instead of the opposite. High exposure was on the bottom and no exposure was on the top. So my odds ratio was 2 over 173 divided by 4 over 100 over 29. So the odds of getting lung cancer if you're not exposed is 8% of what your odds ratio would be 8% of what it would be if you are exposed. You know, I really should have done it the other way around. If you invert this, put 1 over this, you'll get the odds ratio as a number, large number. Okay, and you know, one or something. I'm going to recode this. I'm going to redo this. I'm going to transform, recode. I'm going to recode in the same variables this time. Highest, move that in there. Old variables, and I'm going to say 0. If it's 0, make it 1. I'm just going to switch these two around. And if it's 1, make it 0. Continue. Okay. Okay, here's my new variable. Actually, it's the same variable. I'm going to analyze again. Analyze descriptive statistics. And I'm going to go into crosstabs. I'm going to do the analysis again. Okay, and this time you can see that since, if you look at this, now no exposure is at the, let's see, I got the wrong one. Just guess it. High exposure, no. Oh, you know, I didn't change the coding. That's what happened here. I got to change the coding now. Since I changed that, I got to change the coding, right? This now is value 1. Won't let me change it. So the value 1 is let me think about this. Let's see, what did I just change it to? I want the lower number is, I want, no exposure is 1, good. Now I want, okay, let me recode. I want that to be 1. I want that to be 0. Okay. Okay. 1 represents no exposure. 2 represents high exposure, highest exposure. Oh, sorry, excuse me, 0 represents highest exposure. Okay. Cancel. Remember to add, click add. Okay, let's see if I got it right this time. Analyze to descriptive statistics, crosstabs. Okay. And yes, I got it right. Okay, so what does this say? The highest exposure was 12.1%. The no exposure was only 1.1% getting lung cancer. So the relative risk is 12.1 over 1, or about 12, about 11. And the odds ratio is 4 over 29 divided by 2 over 173. It's going to be similar. So let's go look at our risk ratio. So here's our odds ratio is 11.9. And since it's we know that it's different, we know that we can reject the null hypothesis because the chi-square test was less than 0.05 significance. And here, with our confidence interval for the odds ratio, well, the odds ratio, if there were no difference between exposure and not exposure, then the odds ratio and relative risk would be equal to 1. And since the 95% confidence interval for the odds ratio and for the relative risk does not include the number 1, we know we can reject the null hypothesis. Okay, a little confusing there. I confused that a little bit by not labeling those in a little bit better manner than would have been where they would have been easier to understand. So that's our chi-square. The other thing that might come up is, and remember now, since you're not going to be working with SPSS, most of the time you will be interpreting a study that had a result, or you will be, and this is for the brick and mortar guys, you will be, you will be uh, uh, interpreting output from SPSS, right? Now, if you guys that are online, you guys have SPSS at home, so you know you have it working and you're on computers and so on and so forth. When students in the brick and mortar class are working, sometimes the hardware can be a little uncooperative. So we try and avoid during a test having them do the actual calculations using SPSS and instead give them the outputs and have them interpret it, because we can't rely on all 30 or 40 laptops to be working the same as efficiently as possible. Sometimes they run slowly, disadvantaging one student. Sometimes they crash, and so on and so forth. So that's why we do that for the brick and mortar guys. So at any rate, so let's go move on to analysis of variance. Sometimes, you remember we did the t-test where we looked at the possibility that we wanted to compare two means. Well, what about if we want to compare the means of three groups instead of two groups? So let's go back to our North Carolina birth samples. And let's go in here and let's take a look at somewhere where we have three categories. For instance, perhaps here by the race of the mother, how many categories we have for that? We have lots of categories for that. How about maybe we'll find something a little bit smaller than that? How about Hispanic mother? But that's also a lot of categories. I just want to make sure we have categories that have enough people in every group. So how about this one? Okay. Race of the mother, Hispanic, mother's Hispanic, ounces, low birth weight, premature. And how about ethnicity of the mother? So in this one, we have four groups: non-Hispanic white, non-Hispanic black, Hispanic, and other. I'm going to choose this one to work with. I want to see if the mean for birth weight for non-Hispanic white women, non-Hispanic black women, Hispanic women, and other women, if the means of all three of these are equal. So my null hypothesis would be the mean for non-Hispanic white women is equal to the mean for non-Hispanic black women is equal to the mean for Hispanic women is equal to the mean for all other women in this group. The answer of the odds ratio should be in fraction or decimal form. It probably should be in decimal, right? You calculate it. It's calculated based on a the number of people that are actually the counts in the crosstab table. So it would be for instance, 2 divided by 49 over 7 divided by 150, right? It's calculated as a fraction with whole numbers because they're real people that are being counted. So it's always going to be a whole number. But you report the odds ratio fractionally. Like, in other words, it might be, if there's no difference between the two of them, it might come out to be 1. So the same rate for each exposure, right? You divide the odds of the exposed over the unexposed, same rates would come out to be 1, or it might come out to be 2 or 2.3 or 0.97, or as you saw before, it could come out fractionally, like 0.08, meaning that since I had the non-exposed group on the top row, it calculated the odds ratio based on the top row, the non-exposed. So what it was telling me is that the odds ratio for the women that were not the workers that were not exposed is 0.08. In other words, they're at 8% of the risk that the population that was exposed is. In other words, not being exposed is protective. So it could be less than 1. It just means it's protective rather than a higher risk. Okay, and that's really just a matter of which one you put on the top row, the exposed or the unexposed. So I'm going to go ahead and I'm going to take a look at this, the means for those three women, and my null hypothesis would be the mean for group 1 is equal to the mean for group 2 is equal to the mean for group 3 is equal to the mean for group 4, and I'm going to take a look at those from with that as a null hypothesis. And the alternative hypothesis is that not all of those means are equal. In other words, that at least two of those means are not equal, right? Doesn't have to be all the means unequal, but at least two of them. So the way I would do that is go to Analyze. I would go to Compare Means. It is comparing means. And I would go down to Analysis of Variance. And for our purposes, we're looking at, again, the birth weight of the child, right? And our factors are going to be the ethnicity of the mother. Okay, those are those four categories. And I'm going to ask it to just go ahead and do that first. And I'm going to take a look at my analysis of variance. And my analysis of variance tells me that these are the sum of squares between the groups. These are the sum of squares within the groups. 3 degrees of freedom, divide that by 3. The mean squares between is this. The mean squares within is this. This number divided by this number, divided by degrees of freedom. And the F score would be the mean square between the mean squares within, which is equal to 8.22. And for this number of degrees of freedom, it turns out that our result is statistically significant. This is less than 0.05, so I can reject the null hypothesis that the four means are equal to one another. Now, which ones of the means are different? So now is where we go up here and say, instead of saying just analyze compare means one way ANOVA, now we're going to go into post hoc and ask it to do a post hoc test, usually 2 key. For our purposes, most likely, I'm going to say OK, and it will actually now compare to do a after the fact test to compare which of the means are different. So if I look over here, I'm looking for the ones that have a significance less than 0.05. So we can say with 95% certainty, less than 5% chance of being wrong, that the mean birth weight for non-Hispanic women is not equal to the mean birth weight for Hispanic women. And that the mean, and this is just a duplicate of the one above, right? It just does every permutation. And here's another result. We can also say non-Hispanic black women is different than the mean birth weight for Hispanic women in this particular study, and so on. And it was as far as other and non-Hispanic black, it was a close call, right? It's pretty close to rejecting the null hypothesis there and saying that they're significantly different. All the other women in the study versus non-Hispanic black. Okay, so the post hoc test would give us a view of which of the groups have different means, not just that there's at least 2 that have different means. Of course, if your initial analysis of variance doesn't come out significance, in other words, if this were greater than 0.05, you wouldn't be able to reject the null hypothesis, and you wouldn't bother doing the multiple comparisons. Okay, the last thing, and I'm not sure how much of this will be on the test, is correlation and regression. Okay, and if I can find something, I'm gonna work with the mother's age and the weeks of gestation. How about weeks of gestation and the amount of weight gained? Okay, I can calculate the correlation there. Analyze, correlate, bivariate. I'm going to move the 2 variables in there. I'm going to be looking at the weeks of gestation, completed weeks of gestation, and I'm going to see if there's a correlation between that and the weight of the child. I sure would think there is, right? Let's take a look at that. I'm going to click OK. And I didn't bother to do a scatter plot, but let's see what my result is. Well, my Pearson's R value is 0.83, and it's statistically significant. In other words, I can say with 95% certainty, less than 5% chance of being wrong, that the correlation is not, the Pearson's correlation is not 0, no correlation. It significantly is a correlation different than 0, and it appears to be like 0.58, like a pretty good positive correlation. Let me do a scatter plot now. Could have done it first if I wanted to. Simple scatter plot. And I'm going to move the weeks of gestation into the x-axis and the weight of the child into the y-axis and get a look at what this takes. Get a look at this. Okay, and let's get a look at that graph. And sure does look like there's a pretty strong correlation here, right? So there's a few outliers there, but it looks like a very strong correlation. Okay, so I'm happy with this. Now I can create a line of regression or calculate a line of regression. In other words, create a formula which gives me the line which estimates the relationship between these two numerical variables. Okay, and let me see, I don't want that one. There it is right there. That's the line, my best fit line that estimates the relationship between these two. And I can go ahead and do calculate a regression, a simple binary regression, correlation. I'm going to go down to regression and go to linear. And I'm going to say to myself, okay, the dependent variable is the one I want to predict. So that's going to be the weight of the child. Okay, my independent variable is going to be the weeks of gestation. I want to know if I can predict the weight of the child based on the weeks of gestation. And I'm going to say, okay. And SPSS is going to create it's going to do an analysis of variance, and there's a significant correlation between these two. We know that already, and it tells me that the unstandardized coefficient for the formula for that straight line is 4.837, and the y-intercept is minus 70.411. So in other words, we have created a formula that says that the weight of the child is equal to 4.837 times the weeks of gestation minus 70, and that's a formula we can use to calculate the weight of the child, right? This is the slope, 4.8737 times the weeks of gestation, and this is the y-intercept, minus 70. And that's equal to our dependent variable, the weight of the infant. So we can use this formula. Notice it's that particularly the slope, the completed weeks of gestation slope is statistically significant. Okay, so now what does that tell us? That tells us for every week more that the baby is not born, it will likely be 5 ounces heavier, right? So it makes a big difference, right? So if a baby is born a little bit premature, it's going to be a smaller baby, right? Which is problematic if it's too small, right? So we have a measure of what the impact is of making sure that gestation goes to completion, or if it's starts too early, what the impact would be on the weight of the infant. Okay, so now the only other thing that might come up is that we might be interested in examining more than one variable as a predictor. For instance, we looked at the completed weeks of gestation. Maybe there's something else there that we could also look at. Regression, except this time, let's see, I'll say linear regression. See if there's another one here, another numerical variable. How about the age of the mother? Maybe that has an impact on this too. So we're adding that into our formula, right? We're going to look at whether the mother has an impact. The age of the mother has an impact as well as weeks of gestation. I'm going to click OK. Okay, and let's see what we wound up with here. And now we have a formula that's based on 2 variables that we have measures of. So the formula now is going to be the weight of the infant is going to be equal to 4.8 times the weeks of gestation plus the age of the mother times 0.587 and then minus 85 for the constant. And if I go back up here, you may have noticed before that we had an estimate for the reliability of this sample. So R squared is, I'm going to use adjusted R squared, basically the same thing, 0.339. In other words, this is the this model that we have with the one variable, just the weight, just the number of weeks, accounts for 34% of the variability in the weight of the infant. Other factors represent the other 60%. Well, are we any better off here? What about this model? How does it? How good is it at predicting? Let's take a look at the at the uh, R-square value. The R-square value here is 36%. Before it was, I think, 34%. So this is a little bit better. Not tremendously better, but a little bit better at predicting the weight of the infant, at least accounting for the variability in the weight of the infant. Okay, so that would be what we call multiple regression. There is also logistic regression. Logistic regression, I don't think you're likely to come up with anything on the test. All that's going to be an issue for next week for your various projects and stuff like that, particularly brick and mortar guys, because you're being asked to, do that for you guys online. We're going to cover that in the last week. You'll have the choice of, doing an exam that includes that or completing that project. Okay, in the online course. Um, uh, and you have the parameters for that as well. Okay, so I'm going to call it a night. So I hope this rambling kind of cover everything in a short period of time at least gives you a foundation and just maybe stimulates your memory on what we covered since the last exam and kind of keys you into what might turn up on the exam.